All right, let's get into a story. Back in 1993, a couple of conference papers came out that, quietly introduced this totally brilliant new way to understand the microscopic world. And the cool thing is, it wasn't about building a better, fancier microscope. Nope. It was about building a better way to see with the microscopes we already had. This is the story of roughness spectroscopy. So it all kicks off with a really simple question, a question you and I ask all the time, maybe without even thinking about it, just by touching something. Is this surface smooth or is it rough? Seems pretty straightforward, right? One or the other.
Well, here's the twist. When you zoom in on a surface with a powerful scanning probe microscope, that simple question gets a really complicated answer. See, at the nanoscale, everything has texture. Everything has bumps and valleys. So that clean line between smooth and rough, it just completely falls apart. And that creates a massive problem.
The challenge, really, is this overwhelming flood of information. You have to understand, these microscopes don't just take a pretty picture. They're creating a detailed topographical map made up of literally millions of super precise height measurements. Just to put that into perspective, a single typical image from one of these microscopes can have 250,000 data points, 250,000 numbers just to describe one tiny little patch of a surface. I mean, where do you even start trying to make sense of all that? Well, for a long, long time, the answer was kind of unscientific, to be honest. As the researchers themselves put it, even with all this amazing quantitative data, the final call was often left to qualitative intuition. In other words, scientists would just kind of look at the pictures and guess. They'd eyeball it, which is not exactly what you'd call rigorous science. Now, look, it's not that they weren't trying to analyze the data properly. The standard tool they had was called a Fourier power spectrum, and its job was to break down the surface into a bunch of simple waves. But there was a huge fatal flaw. For pretty much any real-world surface, this method just squished all the most important information together. As they wrote, it was pressed into the plot's origin, which basically made it impossible to read. Imagine trying to listen to a full orchestra, but every single note from every instrument, the violins, the cellos, the trumpets, all of it, was crammed into one single inaudible second right at the very beginning of the performance. That's kind of what looking at these old plots was like. All of that rich, beautiful detail was in the data, but it was completely hidden from view. And this is where the breakthrough happens. The researchers just decided to ask a totally new question, a question so simple, so direct that it changed everything. They asked, over what lateral size scales is the roughness distributed? Now, RMS variation is just a statistical way of saying roughness. So instead of trying to get one single number for roughness, they asked, how much of that roughness is coming from big features, how much from medium-sized features, and how much from the teeny tiny ones? And the answer to that brilliant question is roughness spectroscopy. It's a method that takes the total roughness of a surface and just carefully breaks it down. It plots out exactly how much variation, how much texture you have at every single different size scale, from the nanometer level all the way up. What they did, essentially, was create this powerful new kind of ruler. It was a ruler that could precisely measure not just how rough a surface was, but the actual character of that roughness across all of its different scales. So you can really see the difference here. I mean, the clarity is just night and day. On the left, you've got the old way, the power spectrum. All the important stuff is just jammed down at the beginning, totally unreadable. But then on the right, you have the new roughness spectrum, and suddenly all that information is spread out. It's intuitive. You can actually see clear peaks and patterns that match up with real features on the surface. And this new clarity led directly to real, actual insights. For instance, the new plots could easily tell the difference between a surface made of sharp little bumps and one made of softer, wider ones. It could even figure out the general shape of the features, like are they more like pancakes or more like little rods? It turned a blurry, confusing picture into a sharp, quantitative measurement. But here's where it gets really clever. This new tool had some pretty surprising uses. And the first one wasn't even about seeing the sample better. It was about diagnosing the microscope itself. It was a quality control check. So they ran this simple test. They took an image of the exact same spot on a surface, twice. The first time, they did a slow, careful scan. The second time, they did a much faster scan. Now, in theory, those two images should look identical, right? Well, they weren't. The roughness spectrum of that fast scan showed something the naked eye might totally miss. A structure that was, in their words, drastically more anisotropic.
All that means is it had a strong directional pattern, kind of like the grain in a piece of wood. But here's the thing. That pattern wasn't really on the surface at all. It was a feedback loop artifact, an illusion, created because the microscope's tip was moving too fast to accurately trace the bumps. The tool was actually revealing a flaw in how it was being used.
Okay, so spotting unwanted changes is useful, for sure. But the real power came from tracking the changes you want to see. For the very first time, scientists could quantitatively watch a physical process unfold over time. To prove it, they took a copper surface and dipped it into a silver plating solution. They took a microscopic snapshot after just 5 seconds, and then they took another one from a similar process that had been running for a full 60 seconds. And the results, which you can see summarized here, just brilliantly show how powerful this technique is. The analysis didn't just say, oh, the surface got rougher. No, it showed exactly how it got rougher. You can see in the table, after just 5 seconds, these little 50 nanometer mounds had already formed. But by 60 seconds, a whole new feature showed up, a large-scale directional pattern, maybe from a crack forming nearby. The takeaway from this is just huge. Scientists could finally move beyond just, watching stuff happen. They could get precise numerical data on dynamic processes like crystal formation and surface growth as they were actually happening. It was a total game changer. So, at the end of the day, this was never just about making a prettier graph. It was, as the authors called it, a shift in paradigm. It was a brand new way of asking questions that unlocked hidden information in data that people already had. It gave them a whole new level of quality control for their own instruments, and it turned microscopy from a static snapshot into a dynamic movie. Which kind of leaves us with one final thought. Back in 1993, just asking a different question unlocked a whole universe of information that was hiding in a single image. It really makes you wonder, what other profound insights are hiding in plain sight, in all the data that's all around us, just waiting for someone to come along and ask the right question?